Alright, hell yeah. So this is the physics book that we're using. This is chapter 7, you know what I mean? It is this problem right here. And it says a small particle of mass is pulled to the top of a half a cylinder. And it's got mass and gravity is downward. And we want to know two things. We want to know if the particle moves at constant speed, you have to figure out the force that takes this particle at constant speed. And let's say it was just on a flat surface and we're pulling it at constant speed. Once we get it up to constant speed, you don't need any more force. So that's the first thing with any physics problems is like, what do we know from the basics? Well, is that a force, F equals ma. If you want to accelerate a mass, you put a force on it. But if a mass is already going at constant speed, no force is required. You know what I mean? And so once this mass gets up to here, it's basically kind of going flat. You know what I mean? So the force at the very top is 0. That's how you can take a circle. Anytime you get a circle, put a circle into 3 parts. You're like, this is totally vertical, this is totally flat, and then maybe there's something angled. But at least do the start and the finish. This is totally flat, no force is necessary if we're trying to keep this particle going at constant speed. You know what I mean? And then nothing, and then this is totally vertical. Like it's basically like taking this mass and then pulling it up using gravity. And we know, and so for this problem, we know that force is equal, work is equal to force times distance, and the force of gravity is mg, mass times 9.8. And so the distance that you would take it, well, so it seems just from like if you take this problem down to its basic, put the mass here and then drag it up to the top, what's that going to be? Your work's going to be the force, mg, times the distance, times r. So work is mgr. And then so keep that in mind. That's basically the answer in the end. Because part 2 is just like, okay, so if you're pulling this way with this force, keeping this speed constant, what is the work done by this force? And I don't even think it matters. It doesn't even matter if this is constant, and let's say the speed changes. The work is the same, because the work is just like the force that you're pulling on this thing times the distance it travels. And the distance in this case is going to be from here all the way to there. So that's the other thing. And you can take forces and put them in there, and you know what I mean, you can say, hey, if you're pulling in this direction, it's going to be, you know what I mean, the distance it takes to go from, anyway, let's take a look at this one. And so this is what I did. I mean, this is totally, I had no idea how to solve this, and we used 8 pages to get there. So I think we can get there fairly fast. So let's sit down and plug away at this. Alright, hell yeah. So I said a huge note right here is that if this semicircle is horizontal and this speed is going constant, you won't need a force, because we already did that one. If this piece of mass just travels along a flat surface, you don't need a force. So if this hemisphere is perpendicular to gravity, yeah, you won't need a force. If you already got this mass up to a constant speed, you don't need a force to keep it at constant speed. Anyway, so that's the first one. And then the semicircle is horizontal. So anyway, and then let's just get to it. So what I did here, though, because we're dealing with circles, anytime you're dealing with circles, you know what I mean, the basic thing with acceleration is the acceleration of this particle is going to be the acceleration towards the radius and its tangential acceleration. And from the given problem statement, it says, hey, this is going tangentially at a constant speed. So it isn't changing its velocity. And that's the other thing. Holy frickin' A. You always need to know acceleration in physics, usually, but you really just simply need to know it's the change in velocity. You know what I mean? It's just, you're changing velocity. And to change velocity, you do need to change time. It's the same thing as, like, what the hell is velocity? Well, it's a change in position. And unless you're using quantum mechanics, you cannot change your position without having a change in time. So it's like, it goes hand in hand. Anyway, but in this case, this is just 0. No tangential acceleration, but you do have an acceleration towards the radius, because in any motion, any mass that has a motion wants to go straight. If it is curved, well, that's space-time. That's Einstein. That says, hey, we don't know gravity, no one does, but it's out there, and it's a force. And so this mass definitely just wants to go straight, but it's being pulled towards the middle. Why? Because, well, just in this case, you could have a string on this mass, but in this case, gravity is pushing it down towards this middle, but anyway, when you start to pull up on this, when you start to pull on this string this way, the velocity is directly tangential. You know what I mean? You have a velocity going up. Got it. And if there was no other forces, let's say this was just in deep space, it doesn't matter what direction, there's no gravity, and you have the mass here around a semicircle, and you just pull on this, just really quickly, well, hell yeah, and then let go of the whole rope, the whole system. This mass is going to go this direction, and then take the string with it. It ain't going around this corner. The only thing that's sucking this thing around the corner is gravity, or if it was attached to a string. Okay, cool. So and let's say it is attached to the string, but you still, let's say this mass is just traveling this way, and then all of a sudden, you attach it to a string, well, it's going to go in this arc. It wanted to go this way, but now it can't. It has to change its direction towards the middle. But right here, it has no velocity towards the center, and that's the most important part. All its velocity is this direction. None of it is this direction. But at a certain point over here, you're like, whoa, the velocity should be all this way, but it's not. You actually went back towards the center. So this change right here is back towards the center. And so anytime I do a circle problem, you don't have to do this, but we derive where the hell that comes from. And so let's take a look at that. All right, hell yeah. So I think this page is too much to handle. But no, it gets us started. So we start with, well, you have to use, I like to use radians, because here's the actual answer. The acceleration back towards the center is the radius times the angular velocity, it's radians per second, squared. Okay, now how do you derive that? Well, first just pick an angle, and we did 0.5 radians. Okay, and all that means, that's the other thing. When you're dealing with circles, let's just say this is a radian, this little angle. Radians times radius equals something normal. You know what I mean? And in this case, it's going to be this arc length. And then if you have this, radians per second times radius is equal to something normal. Yeah, it's going to be velocity. So radians times radius is equal to velocity. Radians don't sound normal at all, but you multiply it by something normal, like the radius, hell yeah, you get something normal, like the arc length or the velocity. And if you have angular acceleration times radius, well, you just get normal acceleration. Got it. And this would be the tangential. So yeah, this tangential acceleration would be the angular acceleration, that's radians per second, and then times the radius, something normal, you actually get tangential acceleration. But this one comes just out of the blue, and like we already proved it. We already said, hey, if you're going this way, you had to accelerate back towards the center, and you did so. You did so at r omega squared. You know what I mean? So let's prove it. So here's the proof. Okay, so we have 0.5 radians. That means that this, and then we're just going to say the radius is 1. So perfect. So this distance right here, the arc length is just going to be 0.5 radians times radius. It's just going to be 0.5 times 1. It's going to be 0.5. So perfect. So you have 0.5 meters here. And now we're going to also say that, what are we also going to say? We're also going to say that maybe we're going to say this, that this arc length right here, is if the straight up length, what the hell are we going to say? Whoa. We're gonna, damn it. I think, man alive. Okay, so yeah, this is where I got messed up. You have to, so once you do, you're going to have two components here. You're going to have this total length right here, but if you do go up to 0.5 radians, you already went, so this change in distance right there, that is what happened. So what we do is we pick also radians per second. And we're just going to say this is 1 radian per second. And we only have 0.5 radians. So let's just go to this picture. This picture might make the most sense. Let's throw some more time on the clock. Okay, this is you can use small angle theorem, which says sine of an angle is equal to the angle. Okay, and the other thing is, oh man. The other property that I use in like the next page is also that cosine of angle is also cosine squared over 2. Well, it's actually 1 minus cosine squared over 2. But let's just get to it. So what we want to find out is this distance right here. Because we said if you go 1 radian, we're going to go up this far. So so here's our half circle. Is that and we're going to say in 1 second. In 1 second, we're going to go 1 radian. That means we're going to go this arc length in 1 second, and we're going to go and so and we're going to say that 1 radian, because there's 6 radians in a circle. So 1 radian is approximately 60 degrees. So now we're looking at, this is the sine of 60. So this distance is, oh, and that's the other thing. I think instead of calling this 0.8866, which would be the sine of 60, we just call it 1. Like, hey, you go up 1 and then you go over a half. So I think that's what we do. Ah, damn it. This video sucks. But anyway, maybe, you know what I mean? We don't have to drive this stuff today. Did I even drive it? Yeah. It's just really hard to, you know what I mean, go back through all this stuff. But anyway, oh yeah, and then we use, because this is radians per second. You know what I mean? What the hell is a radian? You know what I mean? Could you have diameters per second? Yeah, you could have revolutions per second. So so here, instead of using radians per second, I change it to revolutions per second, and I just equivocate that one revolution is 6 pi radians. Like we said. And does that make sense? 1 circle is 2 pi. You ever hear of that? You know what I mean? And all that means is that you have 6 point, you know, if it's 3.14, you just do that twice. That's where you get 6.28 radians in 1 revolution. So it's approximately 6. But if you do use acceleration, if you want to find acceleration in meters per second squared, but your input is revolutions per second, well then instead of radians per second, you got to convert radians to revolutions, and it's going to be divided by 6. It's 2 pi. But anyway, basically you're going to get this, where you're going to get acceleration is 36 r omega squared. You know what I mean? So there you go. And if you use diameters, okay. So this page actually, yeah, one more time simplified. So let's do it. Okay, so we're trying to prove that this acceleration towards the radius is due because we have we have this tangential velocity, but like we said, it's supposed to only go this way. So in 1 second, if we go up to here, also in that same second we went over here. But the key to this is that the velocity this way, right here, is equal to 0. But then the velocity towards up here has to be like a max velocity. And to actually get the average velocity, velocity average is velocity final, which is Vmax, minus velocity initial, which is 0 divided by 2. So your velocity average is Vmax divided by 2. And now we can kind of go back, because that's basically what we do here, is we start with 0.5 radians, and cool. So you go up 0.5. Man, can I even do this? Yeah, since we simplified it right here, let's just stay on track. And then the distance we travel, in this so we find the average velocity, and and we said, hey, we're traveling this in 1 second. So like this, oh, damn it. Oh, this is so bad. This is so bad. But anyway, because this whole thing was just deriving that. But if you already know that, okay. So yeah, this was just a test to see if I could actually do the math and then explain what the hell I did. But it's just like, nah, it's like hours of like, grinding. But anyway, so what we have here is that we have the mass down here, and basically gravity is the only force on it. And we're just gonna, hey, what's the time component to get to here to there to there? Well, the time component is just gonna be oh man, I don't even want to do this. Oh, this was interesting. You know what I mean? If you do have the mass, if you actually pick the mass up, to here, which because that's the other. What's the other thing? I have no idea. Oh, yeah. You know what I mean? We know that to lift it to here, to there, that's the work you're doing. Because here's your force of gravity, and to do work, your force of gravity, and you're taking a mass, and you got to lift it to there, lift it to there, lift it to there. But because you're going on a circle, this doesn't take you much time at all. So does this. This takes you twice as much time. You know what I mean? So that's what we did here, is like, and that last page. You know what I mean? We said, like, hey, it takes you like 1.5 seconds to do that, 0.3 seconds to go here, and another 0.34 seconds to go there. So that's where, what the hell is power? Well, power is work divided by time. So if it didn't take you very much time, this is small. It's a small change in time. So if you have a change in time that's small on the bottom, and the work is the same, then hell yeah, that's a lot of power. A lot of power. About the same power, and then not very much power because it took you a hell of a lot of time. The change in t gets up to 2 to, instead of 0.3, now it's like 1.5. You know what I mean? So your power goes down. So you're doing the same work, but you're doing it over a longer period of time. So here you go. Here's a mass on a big old thing, and then it takes a lot of power to get up to there, a lot of power to get up there, and then less power to get over to there. But the same amount of work. Same amount of work to get, 1/3 the height, another third the height, and then the final height. And this is our problem. It's a circle, and there's the radius. All right, let's get to it. All right, hell yeah, I think we're doing good because we're basically there. Is what they said. Well, I mean, they give you in the book. They're just like, figure out why the force has to be just mg cosine theta. Well, when this is here, hell yeah. If you wanna pull up on it, you have to pull against gravity, which is mg. So if you want to get it to do anything, your force is in, and then when your theta is 0, cosine is 1. So that's where you get the mg. Now, like we said, once it's flat, it's at a constant speed anyway. If there's your mass, constant speed, you can't put it. So force is 0. So at theta is equal to 90. This better be 0, and cosine of 90 is 0. So there you go. Force is 0. Okay, so now here's the kicker. Anytime you do work, and especially in this chapter 7 stuff, your force is changing, and it's nonlinear. That's why circles are cool, because it's nonlinear. So that's what we do. We kind of just guess. Well, we say, hey, what's the force when theta is 0? Well, it's just going to be mg. And what's the force when theta is 90? It's going to be 0. So you know what I mean? And what's the force when so like the force right here is still about mg. Force right here, well, maybe it's still mg. You know what I mean? That's what we do. mg. But then up here it gets to be like 0. So just a rough estimate is like you're going to be 0, 0, 0 here, but mg 1, 2, 3. And then for most of it, it's going to be mg, and then for this last little bit, it's going to be 0. But, you still got some. So maybe this wasn't a good approximation. But we do a better one right here. I just guess. I say, hey, you're going to be max. You're going to be mg. mg, maybe half mg, quarter eighth. So then we say, hey, there's 1, 2, 3, 4, 5 slices. And we're going to go 1 plus a half, quarter, and an eighth divided by 5. And you get 0.575. Cool, that was our first guess. And that was pretty good. And so if we do 0.575, times pi divided by 2, hey, we get 0.903 mg. But then I wanted to go a little bit further because I knew this was wrong actually. Because if you go 45 degrees, cosine of 45, well, it's 0.7, which is not a half. It's 3/4. You know what I mean? So this is 1 3/4 half, an eighth. So then do I do a better estimate? Well, hell yeah. So here we go. So I just throw in the fact that this is 0, and then you're gonna multiply by mg. So and then when so here's your angles. Cosine of theta is all these in radians, and then your average in between. So because your force here is mg, but then your force at 10 degrees is 0.985 mg. So if your force here is mg, and then you got 0.985 mg to 10, well, what's the average? So you got to go this plus this divided by 2, and there's your average. So between 0 to 10, there's your average. 0 to 10 to 20, 20 to 30. Let's throw some more time on the clock. All right, hell yeah. So now you got your averages, and yeah, it peters out to 0. But look at this. Just like 1, 1, 1, 1, 3/4, half, half, 2/4. You know what I mean? So even if you just did that, you go, 1, 1, 1, 1, 1, 0.75, 0.5, 0.5, 0.25, 0. So you got 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's do this, because this is very fascinating. So you got, 4 plus 1 plus another 1. Yeah, you got 6. So right off the bat, 6 divided by 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. Divided by 9, that's kind of your average. 6 divided by 9 times 2 pi is, oh, damn it. No. 6 divided by 9 times pi divided by 2. And you get 1.047. Now we got to figure out, because when you're doing work, yeah, it is work in the x direction is force is the average force. Average force in the x direction times the change in distance in the x direction. Yeah, so you change distance in this direction and you change distance in this direction. But since we already made an equation for the force along this line, that's the cool thing about circles. We came up with an equation that says our force is equal to mg cosine theta. You know what I mean? So if we did that, now we know we know the force there and the force there. So work is just the magnitude of the force times that change in distance. And this is kind of arc length. You know what I mean? So if we know the force, that's why if you do stuff in Excel's way better than a calculator. Because you just said the force right at 0 was max mg. And then the force at 10 was 0.85. So the average force in between here is going to be that. And then the change in distance is this arc length. You know what I mean? Which is just theta in radians times the radius. You know what I mean? So you could do that. That's 10 degrees. You know what I mean? It's 10 degrees, 360 degrees, 2 pi radians. That's your conversion. Degrees cancels, blah, blah, blah. You get radians. And then you'll find the distance. And the cool thing about radians is radians times radius is arc length. And if this is... Anyway. So now what? Oh, yeah. So you could do forces in the x and forces in the y, because you have a force in the x, and you have mg, which is a force in the y. But the cool thing about this problem is, hey, let's just find the force on every point here, and then you can integrate. You know what I mean? But I don't do that, because the same thing. This is integration. It's just like, hey, well, let's find the force in between all these, in between 0 and 10. So now we found the average force, and then we found the change in distance, which the change in distance between 0 and 10 is, well, the cool thing about this is if this is the average force between this little thing, you can add these all up, divide by 9, and now you have the average force. Now you have the force average of this thing. It's max here, minimum there. Well, where's the force? The force average might just be at that point, because that's the other thing. you can find the force average, which is 0.635 mg, and you have your F is equal to mg cosine theta. So where cosine theta is equals to 0.63, we can even do that right now. Cosine theta is equal to 0.635. So this is cool. At theta is equal to inverse cosine 0.635, we can throw that into our calculator. More time on the clock. All right, hell yeah. So we do, just make sure we're in degrees. So inverse cosine 0.635, and then we get 50 degrees. So this is cool. So we found, so at 50 degrees, you're going to get the average. This is V average. You know what I mean? You had a max here and a min here. This is why circles, you know, it's not 45. It's not the halfway point. We said there's going to be more force in here, 1, 1, 1, 1, 1, then 3/4, then 0.5. So that's why the halfway, when force is the halfway point, it's going to be 50 degrees. But now this is the average force. So work is just force average times distance. You know what I mean? There you go. The distance traveled. And in this, the distance traveled is the arc length. It's not just this x, you know, change in the x direction or change in the y. It is the arc length. And the arc length of a circle, well, hell yeah. I mean, you can just do the circumference. Circumference is d pi or 2 pi r. So this is going to be 2 pi r divided by 4. It's a quarter of a circle. So it's pi r over 2. Okay, cool. Hey, does that look familiar? Hell yeah, it does. Because if your radius is in radians, this arc length is just this is just pi over 2 radians. You know what I mean? And times radius. You know what I mean? So that's the definition. You know, that's why all you got to know is just, hell yeah, if I have radians and I know this is 2 pi radians, radians times radius is the arc length. It's something, radians times radius is something friggin' normal. And that's going to be, in this case, the arc length. Got it, got it. Okay, so work. After all this, you know what I mean? Now we got force average, 0.635 mg. But now what do we multiply? And I messed up. It's not just r. It's not just r in this direction or r in the. It's pi over 2r. It's a quarter of a circumference. That's pi over 2r. Or it's radians, and the radians, you know what I mean? Radians in half a circle is pi over 2. Cool. And what's 1 radian? Well, it's approximately 60 degrees, but that just says, hey, look at this. This distance along this is going to be the same, equivalent to this radius. Yeah, that's radius times radians. So when your radians is 1 times radius, well, your arc length is going to be 1. Radians of 1 times radius is something normal, and that's arc length in S. And so, yeah, these two things are identical. So at some point, at some angle, they're identical. That's approximately 60. It's like 57 point, who cares? You know what I mean? All right, so, yeah, so we're ready to finish this up. So you get 0.635, and you multiply by pi over 2. And since I messed up and I didn't do pi over 2, I had to change all this. Hell yeah, you get 0.997. This is pretty damn close to 1, and you get work as mgr. You know what I mean? And because it doesn't matter, just like if you have a slingshot and you're like, you know what I mean? Gravity is the only thing, the only force in the universe that gives a damn is gravity. That you got to pay attention to. You know what I mean? There's no gravity sideways. You know what I mean? So when you take a ball and then you slide it up a half cylinder, it's the equivalent of just taking the stupid ball and then putting it on the top. You know what I mean? That's why physics says, that's why using work is way better than figuring out, you know, all the change in velocity. Because if you do F equals ma, which is really cool, you have to find the acceleration at every friggin' point. Where if you do work, all you have to do is say, hey, force times distance, and in this case you identify that the only force working on this stupid thing is gravity, so it's mg, and your distance is just the distance in the force direction. You know, so even if you're pulling sideways, that's kind of the oh aha moment. And I don't even solve it right, because what you would do is you would get F equals mg cosine theta, and then your D is going to be well, I think it is like it's this arc length, but then you got to integrate. You know what I mean? So that's for another video. I don't do that. You know what I mean? You might as well solve it in Excel and learn this way. So anyway, I'm about done. And this is definitely a little bit of a manic video. But we got to go fast as hell if we're just throwing out trash content until we figure it out. But this was fun. You know, 8 pages just to get the right answer from like hey, I don't want to integrate. That's what happens. If you know how to integrate, you can get there in about two swipes of the pen. If you don't know how to integrate, you do it this way. But this way is so much better for your brain because you understand what the hell integration is. And I still don't know what it is. But it'll help you get a little bit closer. Alright, well thanks for joining me. Hopefully this was fun. And guess what? That's a video.